Marhaba. Okay, in this session we want to talk about another relation between integers. Remember, we talked about the divisibility of integers. We said m divides n if n is equal to k times m, where k is an integer, which means we can take k steps of length m to get to n. Now we want to see another relation between the integers, which is called congruence. Okay, so what is, let me define it here. What is this relation? So let's choose any two integers whatsoever. So let a be an integer and b be an integer. And let m be a positive integer. Okay, so you can think of m as a fixed positive integer and a be any integers you want. Then we say that a, the integer a, is congruent, this is how we write congruent, 3 horizontal bars, to be modulo m. Okay, so this is the relation I am defining. We say that a is congruent to b modulo m if and only if, so this is a definition, m divides the difference between a and b. Okay, so this is a relation which says that two integers a and b are related through this relation. So we say a is congruent to b modulo m if, when you look at the difference between a and b, and you find out that the difference is divisible by m. So m divides a minus b. Okay, and let me say how do we read this again? So this is read as a is congruent to b modulo m. Okay, so congruent, this is the symbol for congruent. Okay, so let's take examples. What do we mean by this relation? Let's look. Do you think 17 is congruent to 5 modulo 6? So the answer is yes. So first notice that a is congruent to b modulo m is a proposition. It's a statement which is either true or false. Either m divides the difference between a and b or not. So let's see if this is true. This proposition is true because 6 divides the difference, 17 minus 5. Because 17 minus 5 is 12. And 6 divides 12 because, why 6 divides 12? Because we can find an integer k which is 2 such that 12 is equal to k times 6, so 2 times 6. Okay, so we know that 17 is congruent to 5 modulo 6. Okay, let's take another example. So do you think 17 is congruent to 11 modulo 6? So the answer is yes. So this is true simply because 6 divides the difference, which is 17 minus 11, and which is 6, and 6 divides 6 because 6 is equal to 1 times 6. So this is k from the definition of divisibility. Okay, let's take another example. So look at the example 33 is congruent to 18, okay, modulo 2. So is this true or false? So what does it mean? It means that 2 divides the difference, what is between 33 minus 18. So this is true if and only if 2 divides the difference. What is the difference? It's 13, right? Sorry, it's not 13, but it's odd anyway. So it's 12 plus 3 is 15. Okay, and this is false, right? This is false. 2 does not divide 15 because we can't find the k such that 2 times k is 15. Or another way to say it, that 15 is odd, but 2k is even. So this is false, and this is how we say that 33 is not congruent to 18 modulo 2. Okay, let's take another example. Okay, what is the other example? 10 is congruent to 45 modulo 7. Okay, so this is true. So by definition, if and only if, what does this mean? 7 divides the difference, which is 10 minus 45. And this is true if and only if 7 divides negative 35. But this is true. What does it mean that 7 divides 35? It means that there is an integer k such that when we multiply k by 7, we get negative 35. And what is this number? It is negative 5. So since this is true, since negative 35 is equal to negative 5 times 7, then this is true. So we know that 10 is congruent to 45 modulo 7. Okay, let's take another example. So do you think any number, say 7, is congruent to itself modulo any number, any integer, say 4? So this is true. Why? Because 4 divides the difference, 7 minus 7. And what is the difference? 7 minus 7 is 0. Okay, and 4, so this is if and only if, and 4 divides 0. Why? Because 0 is equal to some integer k times 4, and this integer is 0. Okay, so any number is any integer is congruent to itself modulo any positive integer. For this reason, because the difference of any number with itself is 0, and any positive integer divides 0. Okay, let's finish with this example. Is 28 congruent to 19 modulo 3? So the answer is yes. This is a true statement because 3 divides the difference. And what is the difference? 3 divides, the difference is 9. Okay, why 3 divides 9? Because we have an integer k, in this case it's 3, which when we multiply it with 3, we get 9. Okay, so I hope the idea of congruences is clear now. So this is a relation between the integers, which we say that an integer a is congruent to an integer b modulo m, if and only if, this is a definition, m, this is m, divides the difference. Okay, now let's take a very nice theorem which allows us to look at congruences from a different point of view. So let me write here a theorem. So let a be any integers you want, and let m be a positive integer. Then the following is true. A is congruent to b modulo m. Okay, what does this mean? That m divides a minus b if and only if a mod m. What is a mod m? Remember, we divide a by m using the division algorithm and we take the remainder. So this is the remainder of dividing a by m is equal to b mod m. Okay, so this is a theorem which says if this is true, then this is true, and if this is true, this is true. Again, what does it say in words? That a is congruent to b modulo m if and only if the remainder after dividing a by m is equal to the remainder of dividing b by m. Okay, so I will not do the proof here in this video, but you have an exercise. So read the proof from the notes. Read the proof from the notes. from the lecture notes, but let's have some examples here. For example, let's take a statement of this form which is true. Say, for example, 17 is congruent to 5 modulo 4. Right? Because 4 divides the difference. What is the difference? 17 minus 5 is 12 and 4 divides 12. Let's see if this statement is true. So let's compute what is 17 mod 4. So what is 17 mod 4? What is the remainder of after dividing 17 by 4? Remember, we can write 17 in the form of q times 4 plus r. And here is 4, q is 4, and m is 4 plus the remainder 1. So we know that 17 mod 4 is 1. And now what's 5 mod 4? 5 mod 4 is, let's divide 5 by 4. So we need only one step of length 4, we reach 4, and then what will remain is also 1. So here the remainder is 1, and so see that the remainder of dividing 17 by 4 is the same as the remainder of dividing 5 by 4. So since this is true, they have 17 and 5 have the same remainder after dividing by 4. Okay, let's take an example in the reverse direction. So choose any two numbers, say let's see, what's 20 mod 3? Then what is the remainder of dividing 20 by 3? It is 3 times 6 is 18 plus 2, right? And see that 2 is still less than 3. Okay, let's take another example, another number, which is after dividing by 3 we also get 2. Okay, so for example, look at 8. Right? 8 mod 3 is 2. When we divide 8 by 3, we take 2 steps of length 3, we get to 6, and what is remaining is 2. Now since 20 and 8 both have the same remainder after dividing by 3, then we expect that 20 to be congruent to 8 modulo 3. So is this true? Is 20, what does it mean? So this is true if and only if 3 divides the difference. 20 minus 8. And what is 20 minus 8? It's 12. And does 3 divide 12? Yes, 12. Yes, because we can find an integer k such that when we multiply it by 3, we get 12, which is this integer is 4. Okay. So here shows if you choose two numbers, 20 and 8, and you divide them by 3 and you get a remainder of 2, then these two numbers should be congruent modulo 3, which means 3 divides their difference. Okay, so this is a very nice property of looking at congruences. So here means that m divides the difference, and here means that a and b have the same remainder after dividing by m. Okay, so same remainder. Remember that we defined this was the notation for the remainder after dividing a by m, a mod m. Okay. Now let's take another theorem about congruences. So here is a theorem. Again, let a, b be integers, so a, b are integers, and m is a positive integer. Okay, suppose that a is congruent to b modulo m, and c is congruent to d modulo m. So I forgot to say, and also c, d are integers. So choose any 4 integers and m positive integer, and suppose that a is congruent to b modulo m and c is congruent to d also modulo m. Then we have two true statements. Let me say the first one. Then, if you sum the left-hand side of the two equations sides, it will be congruent to the sum of the right-hand sides of the two equations modulo m. So this means then A plus C is congruent to B plus D modulo m. Okay, so suppose this is true and this is true, then this is true. Let's prove this. What does it mean that A plus C is congruent to B plus D modulo m? It means that m divides the difference. So what does it mean that m divides the difference? We need to show that the difference is equal to an integer k times m. So let's look at the difference. So consider the difference. Consider A plus C minus B plus D. Okay. Now, what do we know from here? That A is congruent to B, so let me write them in green. A is congruent to B modulo m, which means, okay, maybe I should leave some space here. Okay, let me write these two statements. We suppose A is congruent to B modulo m. This means that m divides the difference A minus B. And this means, what does it mean that m divides the difference? It means there is an integer k such that A minus B is equal to k times m, right? And from the second one, we know that m also divides C minus D. And this means that there is an integer L such that C minus D is equal to L times M. So this is our hypothesis. We know this. Now, A plus C, look, let me write this. So now this means that this is A plus C minus B minus D. I want to use my hypothesis, so from here I want A minus B. So I can write this as A minus B plus C minus D. Okay, and this is equal, look, from A, we know that A minus B is equal to Km because we are assuming that A is congruent to B modulo M. So A minus B is equal to Km. And similarly, C minus D is equal to Lm. Now we can take M as a common factor, and then K plus L is an integer because both K and L are integers, so this is equal to, say, S times M. Look, what did we do here? What did we show here? That the difference is equal to an integer times M. This means that M divides the difference of the sums. So M divides A plus C minus B plus D. And if M divides the difference of two numbers, then these two integers are congruent. So this means that A plus C is congruent to B plus D modulo M. And this shows the first property. Number one, the sums are congruent modulo M. Okay, the second property is that, look here, this is our hypothesis. Also, if we multiply the left-hand sides, then it will be congruent to the multiplication, to the product of the right-hand sides of these two equations. So, which means then A times C is congruent to B times D modulo M. Okay, we need to prove this. So prove. So why is this true? What does it mean that these two numbers are congruent? It means that M divides the difference. So we want to show that M divides the difference, right? So let's look at the difference. Let's look at AC minus BD. And we want to show that this difference is equal to an integer times M, which means that M divides it. So let's look at, this is the hypothesis we know. Look, from equation number one, we know that A is equal to B plus K m. So see, from here we know that A is equal to B plus Km. And from the second equation we know that C is equal to D plus Lm. Okay, so we will use these two equations. Now A times C. Now we know from the first one that A is equal to B plus Km, right? So A is equal to B plus Km. And from here, C is equal to D plus Lm, right? Look here. C is equal to D plus Lm. Okay, so here I'm writing A times C, so this is A, this is C, minus BD. And then let's multiply these two brackets. Remember, all of these symbols represent integers. Okay, so B, this is BD plus BLM plus KMD plus KMLM. Or if you want, KLM squared. Okay, minus BD. Let's see here. Now, look, we have BD minus BD, it's 0, and what is left, the three terms have M as a factor, so we can take it as a common factor. Then we'll be left with BL plus KD plus KLM. But all of these are integers, and the sum of them is an integer, so this is, say, M times S. So this means that we showed that AC minus BD is equal to an integer times M. So this means that M divides AC minus BD. But if M divides the difference of two integers, this means that by definition of congruence, the integers AC and BD are congruent modulo. Okay, so we proved this property as well. So again, let me write the statement again. What is the theorem we proved now? That if A is congruent to B mod M, remember that we put brackets for modulo M when we use the congruences, and C is congruent to D modulo M. Suppose these two statements are true, then we know two things are true. Okay. The first thing, that the sum of the sides are congruent, so A plus C is congruent to B plus D modulo M. And two, we know that the product of the sides are congruent. Okay, so A times C is congruent to B times D modulo M. This is what we proved. Okay, let's have some examples on this. Okay, for example, check, is 7 congruent to 2 modulo 5? Which means, does 5 divide the difference? 7 minus 2 is 5, and 5 divides 5. Okay, so this is a true statement. Now look at this. 11 is congruent to 1 mod 5. Is this a true statement? Yes, because 5 divides the difference. 11 minus 1 is 10. And 5 divides 10, because 10 is equal to 2 times 5. Now let's apply, look, what do we know now? We know that if we add the sides, then 7 plus 11, which is 18, must be congruent to 2 plus 1, which is 3 mod 5. Is this true? Yes, because 5 divides the difference, which is 18 minus 3 is 15, and 5 divides 15. Because 5 divides 15, since 15 is equal to an integer 3 times 5. Okay? So since, let's multiply the sides. 7 times 11 is 77, and 2 times 1 is 2. So can you check if 77 is congruent to 2 mod 5? The answer is yes, because 5 divides the difference, which is 75. Okay. Now we can use, we can multiply both sides by 3. You know why? Because 3 is congruent to 3 to itself mod 5. We've seen this in the examples, because 5 divides the difference, which is 0. So this means that if you multiply 3 on both sides, or you add 3 to both sides, then we get a true statement. So let's add, say, 3 to both sides. 7 plus 3 is 10, is congruent to 2 plus 3, which is 5 mod 5. And this is true because 5 divides the difference, which is 5. We also get, say, number 4, we can multiply both sides by the same integer. For example, 3. 7 times 3 is 21, and it's congruent to 2 times 3, which is 6 mod 5. Okay, this is true because 21 minus 6 is 15, and 5 divides 15. Okay, so this is about congruences.